Hello, welcome to another video on differential calculus. And today I'm starting with three definitions. The first one is differential calculus. So we define differential calculus as the branch of mathematics which deals with rates of change of quantities with respect to others. So basically we're defining differential calculus as a branch of mathematics which deals with rates of change of quantities with respect to other quantities, or you can simply say with respect to others. So that would be the definition of differential calculus. But what is the definition of differentiation? So we define differentiation as the process of determining the gradient of a tangent to a curve. It's a process of determining the gradient of a tangent to a curve. That's differentiation. And what is derivative? It is the gradient of a tangent to a curve. It is the gradient of a tangent to a curve. That's derivative. So these three definitions are very critical. I'm going to repeat them. Differential calculus is a branch of mathematics which deals with rates of change of quantities with respect to others, or you can say with respect to other quantities. Differentiation is the process of determining the gradient of a tangent to a curve, and derivative is the actual gradient of a tangent to a curve. Now, I want us to focus on differentiation a little bit more. Our next item is going to be differentiation from first principles. So I have a graph already drawn here for the sake of time. Here we go. So we're now talking about differentiation from first principles. What is differentiation? To remind you again, it's the process of determining the gradient of a tangent to a curve. That's differentiation. And of course, we're basically saying that there are many ways of determining the gradient of a tangent to a curve. One of them is differentiation from first principles. So consider the function f sketched here. The function f sketched on the Cartesian plane, your x-axis and your y-axis there. I want to talk about a point A, and I'm interested in determining the gradient of a tangent to a curve f at point A. So that is the tangent that I'm focusing on. But where do I start from? Do I start from that tangent? No, I start from that secant there. So I originally have a secant, and I move this secant down. You can see the arrows pointing downwards. I move this secant into that position, and I continue moving it. It will come into that position, and finally it gets into the position of a tangent. So the secant eventually becomes a tangent if I continue moving it down until it comes into that position there. But I want you to notice something. With that original position of the secant, if the value of x at A is x, the value of x at B in that position there on the secant and on the function f is going to be x plus h, because that distance from here to there is h. So it will be x plus h. That gives me the value of x at that position, which will be the value of x at that point. And to find the value of y, I have to punch x plus h into f, just like I have to punch x into f to determine the value of y there. So this point A here has the x coordinate x and the y coordinate f of x. That point B there has the x coordinate x plus h. The y coordinate is going to be f of x plus h. So I'm calling this point A and I'm calling that point B. Now, the x values, I'm going to call them x1, y1. And there I'm going to x plus h, I'm going to call it x2. And then f of x plus h, I'm going to call it y2. Now, why am I doing that? Because the gradient of any straight line is given by that formula there. So I want to talk about gradient of the secant. But I want you to notice something. As the secant moves down into the position of a tangent, the value of h decreases. So I put h to show you that h is a variable. It changes. So in the original value of h will be that distance. And as I move the secant down, the value of h will become that distance. And as I continue, it will be that distance. And eventually, when the secant becomes a tangent, the value of h becomes 0. So as the secant approaches the tangent, the value of h approaches 0. Now, that is critical, because for any straight line, that is the formula for gradient of any straight line, change in y over change in x. So y2 minus y1 over x2 minus x1. Now, if we substitute, let me put a subscript to m there, and I'm going to call it m sub secant. I'm interested in gradient of that secant there. I'm going to have to substitute these values into that formula as follows. So what is y2? Well, y2 is f of x plus h. I place in that position, there it is. What is y1? F of x over here. And I place in that position, I get that. What is x2? It's going to be x plus h. I place in that position down there, there it is. What is x1? It is x, and I place in there, and I get this. And if you notice, the x's cancel. In the denominator, I'm just going to have h. In the numerator, I'll have f of x plus h minus f of x. So this is the expression for gradient of a secant. Now, remember, I told you that as the secant approaches the tangent, the value of h approaches 0. And therefore, I can say that m tangent will be the limit of m secant as h approaches 0. So let me write that one down. So I'm going to say here, on my page 3, I'm going to say, therefore, I'm going to say m tangent must be equal to the limit as h approaches 0 of what? Of m secant. Now this is critical. This is absolutely critical, because I'm going to change that notation shortly. Now, changing this into the notation that most of us are familiar with, if I may put this in brackets like that, for example, if I change this into the notation that we're more, maybe some of you may be familiar with, would be this here, m tangent becomes f prime of x, written like so, f prime of x. I'm going to tell you what that one, who started that, or who came up with that notation. This is going to be the limit as h approaches 0 of that expression, m secant. I'm going to replace it with that expression there. I hope you can see it. I'm sure you can see that would be m secant. So this becomes limit as x approaches 0, as h approaches 0 of f of x plus h minus f of x all over h. So this is the new notation or formula for gradient of a tangent. Remember, we're coming from gradient of a tangent equals limit as h approaches 0 of gradient of secant. So written like this. Now, there are two things I want to mention here. That this here is read as f prime of x. F prime of x. That's how we read it. And we know that, at least you should know that this is actually the Lagrange's notation of the derivative of f, of course, with respect to x. But notice something here, that what is the derivative? We said derivative is gradient of a tangent to a curve. And according to Lagrange, the notation, we have different notations. We have Newton's notation, we have Leibniz notation. We'll be looking at those notations when we start looking at rules of differentiation. But in this case, we're focusing on differentiation from first principles. We use Lagrange's notation, differentiation from first principles. Now, determining the gradient of a tangent to a curve by using this formula is what we call differentiation from first principles, as you can see up there, differentiation from first principles. So we're going to be using this formula in some cases to determine the gradient of a tangent to a curve. The question must specify, and then we will be able to use that. So I want to give one example here. Let me go to the next page. I think I'm going to need to move to the next page here. Page 4. So I'm just going to give one example, and then I'll come again with another video where I'm going to look at a few more examples. So example, if you're doing grade 12 in South Africa, this would be a typical exam question, and I believe that even under IGCSE, which is Cambridge, it will be a typical exam question as well. So given f of x is equal to 3x minus half x squared. The question says determine f prime of x from first principles. From first principles, then it means we have to use that formula. Which formula? We will have to use this formula here. This formula here. I want to demonstrate how you do that in the next minute or two. So our answer would be as follows. So I know f of x is equal to 3x minus half x squared, and therefore I'm going to say f of x plus x, f of x plus h, this would be 3 open brackets x plus h minus half x plus h all squared. This is equal to 3x plus 3h minus half. If you have attended my, you've watched my videos on algebra, I've explained how you expand that. It will be x squared plus 2xh plus h squared. Now expanding that, we get 3x plus 3h minus half x squared, half minus half times this here, minus half times 2xh, it will be minus xh, minus half times h squared, it will be minus half h squared. Now I'm gonna go straight to the formula. I'm gonna say, therefore, I know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Substituting, what I have is limit as h approaches 0 of what? Of this expression, this symbol notation here must be replaced by that. So I have 3x plus 3h minus half x squared minus xh minus half h squared minus, and I have to use brackets here in the place of f of x. I must put brackets and then substitute that function into that space there. Without brackets, you would mess up the signs. So this is 3x minus half x squared. Remember, we're supposed to say all over h. Now let's remove these brackets then. Now our next step, we're going to say limit as h approaches 0 of 3x plus 3h minus half x squared minus xh minus half h squared minus 3x plus half x squared all over h. Now notice that these cancel, and that cancels that. So if I collect what is remaining in the numerator, I have limit as h approaches 0 of 3h minus xh minus half h squared all over h. If I factorize the numerator, I'm going to have limit as h approaches 0 of h open brackets. This will be 3 minus x minus half h all over h. These cancel. If I move to page number 5, I check everything that is remaining to page 5 here. Page 5. The remaining part on page 5, I'm going to have the following. If you like, I'm going to have that will be equal to limit as h approaches 0 of what? Of 3 minus x minus half h. Now notice something. As h approaches 0, half minus half h will approach 0, the whole of that. As h approaches 0, this whole part minus half h will approach 0, and therefore my final answer is going to be 3 minus x. So this would be the gradient of the tangent to f of x equals 3x minus half x squared at any point. Remember, x is a variable at any point. It's critical that you understand that x is a variable. So at any point, if I want at x equals 0, it will be 3, because if you substitute 0 here, the value of the gradient there is going to be f prime of 0 will be equal to 3. That will be gradient of the tangent. Please take note of the fact that f prime of x is gradient of a tangent. That is critical. What is differentiation? The process of determining gradient of a tangent to a curve. There it is. That's differentiation, the process of determining gradient of a tangent to a curve. What name is given to the gradient of a tangent to a curve? Derivative. So then we're basically saying that this expression here is the derivative of what? Of 3x minus half x squared. Of course, derivative with respect to x. That's the only variable we have here. So that would be how you determine gradient of a tangent to a curve by using first principles. All right. If you're new to this channel, please subscribe, share these videos. It will help us grow the channel and give us the ability to be able to produce many more videos and help as many students as we can manage. I will come up with another set of videos because this is a very big topic in mathematics, right from grade 12 up to university. At university, of course, you have calculus 1, calculus 2. So I'm going to be looking at calculus 1, calculus 2. If you remember, I have looked at already how to determine, how to prove the existence of a limit by using the precise definition of a limit. But this is way before that. This is way before that. Remember, we've started by defining what differential calculus is, and then we've gone on to look at differentiation from first principles. So I'll come with another set of examples on differentiation from first principles, give you a couple of functions, and then we'll move to rules of differentiation. So when I move away from high school into university mathematics, I'll be able to tell you, for example, proofs of rules of differentiation are actually beyond the scope of high school mathematics if you're doing pure mathematics, not advanced program maths, because in advanced program maths, I think proofs are done, but in ordinary mathematics, proofs are not done. All right, so I'll see you in the next video then.